Okay. So this is about what I was expecting. I know we had quite a few folks that were saying the roads were bad. I did not have that experience, but I know traffic was apparently terrible. Ty got like routed around wrecks and various things between Edmond and Oklahoma City, and that's why Ty is not here right now, as he's still trying to manage his way to get down here. So just drive through Southwest OKC on the back roads and you get around all of these things. All right. So apparently I'm going out of order. We're going on the syllabus order. So the syllabus says we're doing body composition next. So that's what we shall do. Some of this you guys have seen, I imagine, a little bit of this before in Principles of Health and Fitness. But I like to start when we talk about body composition by doing a little thought exercise. Okay. When I say body composition to you, what do you immediately think of? Just yell things at me. BMI, fat mass, a ratio of what, Abby?
Percentage of fat, bone, and muscle.
Fat, bone, and muscle. Okay, way too informed on all of those things. Okay. Anything else? What do you picture in your mind? Indirect or direct measuring. Okay. No? Nobody think of like bodybuilders or, fitness person or cross-country runner or anything. Nobody thinks about those kinds of things? No? Okay, y'all are just way too diligent of students. You've seen all this before. You know what's coming. So you're just running my analogies on a Monday morning. But that's fine. That's great. That's great. So normally, let's see what we get here, right? I feel like when we have done, I don't understand why. Okay, great. It's transcribing. That's fine. When you say body composition, right? Like people think of stuff like this. I love this. Y'all are this is like as old as you guys, like way old, like buy hydroxycut, do P90X. You all know what P90X is, kinds of things. We'll be like, I'm going to go from here to here. But people also oftentimes think of like distance athletes versus football players and all of that kind of stuff. Okay. So what we're going to get into is a little bit of that. Okay. Why do people look and appear in certain ways? But actual body composition is going to tell us much different kinds of things. And so I like to start as well on all of this by being cognizant of the room. We have this many people. There's a reasonable chance that in a class of 85 people, there are people that have eating disorders, people that have something called body dysmorphia and all of that. And so I just want to let everybody know we're going to talk about eating. We're going to see pictures and talk about body composition, what we're made up of. We'll even talk a little bit about some kind of healthy ranges on all of these things. And that may be difficult. Okay. And if it is, talk to me about it. If you need to step out, like whatever we need to do, that all that is okay. All right. I don't want this to be a thing where people are it's gonna kind of be upsetting, but that's a very, very real kind of thing. Okay. It's a very real kind of thing. Okay. So what does body composition actually tell us? Right? What it actually tells us is, what are you made up of? Okay. You guys are all protein and amino acids and free fatty acid, carbohydrate, and a lot of water and these kinds of things, but it tells us what we're made up of. It lets us put some numbers to what exactly is it that you're formed by. Okay? And that can be the chemical or the anatomical makeup. We'll see as we look at different ways of trying to quantify this, how that's going to get split and broken out. Okay? Historically, you guys were correct. Body composition tells us, right, relative fat and non-fat mass or composition of our body. We are X amount fat, X amount, everything else. That's historically what we would learn from all of this. We're getting to a point where the historical things like the Dark Ages, that you guys have not lived in a world where we didn't have DEXA scans, where we didn't have things where we could actually split that non-fat tissue much more accurately into bone and muscle and water and things of that nature. Okay, so we'll get into how we do that and what that tells us there. But that's the much more recent kind of thing. We're much better, as you guys will see. It's fat and then everything else. And the real differences between how we quantify things is how precisely can we split up that everything else component kind of side of things. Okay. So what does body composition actually tell us? Well, at its most basic, body composition is an indicator of your nutritional status. Okay. Are you eating more than you need based upon changes in those things? Are you eating less than what you need based upon those things? Are we in a caloric deficit? Are we in caloric excess? Are we sort of calorically neutral? It can tell us that. Okay. It can tell us that. At our most basic diets and things that change body composition, that's what they're getting at, is nutritional status. Beyond all of that, and where this is going to get to be more helpful, is that it separates the body into metabolically active and inactive tissues. We know muscle, right? We know that muscle drives resting metabolic rates, and we know that muscle drives energy expenditure. And so by better understanding that, we can have a better understanding of what are our nutritional needs, how is that gonna play around if we're training and doing those kinds of things. The other piece now, and this is going to be maybe not new information for you guys, but we're going to emphasize it, is health status. Body composition tells us a lot of things about health status. Okay? About health status. If you want to live longer and you want to have less risk of chronic disease, you need a high VO2 max. Okay? We know that. You need a high VO2 max. You need muscle, so weirdly, your grip strength predicts when you die. Okay? Whatever it is, right? Somebody that doesn't have a lot of grip strength, it's pretty frightening for me. Conversely, if we want to know who is going to be at a greater risk of developing diabetes, cardiovascular disease, certain forms of cancer, pick any chronic disease, it's people that have excess fat. What is excess fat? How much is excess fat? You might ask. We don't have a good answer for that. Okay? We don't have a good answer. But we know the more you weigh relative to your body size, the higher your risk of basically dying from everything. Okay? So we know that having excess fat leads to health problems. Having too little muscle leads to frailty and health problems. Having too little bone mineral density leads to health problems. You will fall, you will break something, and then after you've had a fall and you've broken a hip, your overall mortality rates go up, 500% or some ridiculous amount. Okay? It's a really scary kind of thing. And so understanding body composition helps us to get at where we are with these. Understanding what it is right now today for you guys is actually really, really important. Okay? It's really important. I joke about this. Guys, you've already peaked. Sorry, you've already peaked. You're already past the point where you will have the most testosterone and therefore the greatest driving sort of not having to work at it muscle mass you're ever going to have. Okay? Ladies, your bone mineral density is as high as it's ever going to be. You hit menopause, estrogen falls, bone mineral density gets eaten away. You're going to fall because older adults fall. That's just what happens. It's why we need muscle. It's why we need strength so we can maintain balance and posture. But older people fall. If your bone mineral density is low, you will break something, and then bad things happen. My paternal grandfather fell, broke his hip at like 72. He basically never walked again. Okay. So these are important things for us. Fernando.
So men have already peaked women left.
When? Most of them by 18, 16, 17, 18, just from a testosterone standpoint.
The women, the low bone density is when we hit menopause.
Yes, bone mineral density takes a very, very significant dip after menopause. So you guys have to have done things now to have built up your bone mineral density. It's coming for you. It's coming for you, right? Menopause is usually in the 50s. It's very, very, well, my wife wanted me to tell you that maybe perimenopause is worse. I don't know. So,
But the bone density doesn't affect them there.
as estrogen falls, it affects some parathyroid hormone balance and some different things. Estrogen is protected for bone mineral density. So as it falls during menopause, yes, there's a chance. So you got to have as much as you can have by the time you get to there. You can take all the calcium supplements you want when you're 60, but if you don't have bone mineral density because you didn't do things like run and jump and squat and all of that now, then you're going to have problems. Okay. Aging sucks. That's what I want you all to take away from today. Aging is terrible. Okay. It's terrible. I do not recommend aging. I don't. We'll see some things and I'll be like, we're all going to be a statistic at some point. Okay. How do you get the bone density? Running, jumping, squatting. You have to generate high forces that load the bones. Okay. All right. Now, you guys have all heard of something called body mass index, right? You guys know what BMI is? Okay. Let me tell you what BMI is not. BMI is not. It is not a measure of body composition. Okay? All BMI is how much do you weigh versus how tall you are. That's it. We have some ranges and some of those kinds of things. It makes no distinction on what it is that makes you weigh more or less. Okay? As we like to say, it makes no distinction between overweight, right? Because you have a lot of muscle versus over adipose tissue or over fat, which seems very crude to say. Okay? Body fatness and BMI are only weakly related. Okay? For those of you that know anything about research, they're only weakly related. Here's the problem though. BMI is a terrible measure of body composition, except it's wildly predictive of poor health outcomes. Okay? Poor health outcomes. In a very, very large sample, which we have huge amounts of data on, if your BMI is too high, you are at an increased risk of basically everything. Okay? Because most people, right? We're not talking about every individual, like there are exceptions, but in the vast majority of people, if your BMI is high, it's because of excess adipose tissue, right? It's because of excess adipose tissue. My BMI is not appreciably different from when I was a senior in high school, okay? It's not appreciably different. My actual body composition is wildly different than what it was when I was a senior in high school. Okay? It's very, very different. But so we know in general, though, right? In general, BMI is predictive. And it differs between old people and young people, right? Young people tend to have more muscle. So it's less predictive there. Men versus women, right? There's less of an issue there. But again, women, y'all are penalized because you have essential body fat that we'll talk about. Weight train versus non-weight train. It doesn't make accounting for bone mineral density and all of these things. It's a terrible measure, except it's not. It should not work, except it's wildly predictive. Okay? So I don't have an answer for that. It makes no sense to me, but that's the honest truth. High BMI, right? BMI over 25, increased risk of all-cause mortality and things if you're in the overweight group. BMI over 30, qualify for insurance to pay for the Ozempic. Okay? because of this dramatic increase in mortality. Okay, because of that. There is almost, y'all are gonna be blown away by this because it kills me every day. We have almost no data and no studies on actual measures of body composition and health outcomes because it's hard to get enough data. We can call people on the phone and be like, hey, do you have high blood pressure? Tell us what your height and your weight is, right? It takes tens of thousands of people to do these studies to predict relatively accurately, right, these health outcomes. We can't get tens of thousands of people to come get a DEXA scan, right? To come show up someplace and let us do skin folds on them, which is not great, but it's better than nothing. So we have very little data on body composition and health. It's just the way that it is. I can't tell you X amount of body fat if you're a woman corresponds to that sort of overweight and obese range. We don't really have, we have some sort of guidelines, but we don't have anything like what we do with BMI on all of that. Okay. But BMI is not, it's a measure of size or a measure of volume in almost ways, or surface area, but it's not a measure of composition. Okay. We know BMI of 18.5 or less, you're underweight, that's also a problem. Okay. Normal is 18.5 to 24.9, 25 to 29.9 is overweight, right? If you measure waist circumference, right? So in men, if you measure around the belly button, ladies and y'all, if we measure around basically from where your sternum is and your hips, the smallest area there, which if you're my wife is way up here, right? It's going to be those sort of different things. If you add a measure of waist circumference on top of all of this, it becomes way more predictive. And it's already pretty predictive. This is really, really helpful. Okay. And so you can see increased risk of sort of all-cause mortality in the midst of all of this. If you have men, if you have a waist circumference over 40 and you hit all of these, ladies, if it's over 35, then you can see how this is going to all sort of play out. What we know, as we'll see a little bit later on, it's not really the point of this lecture, is that storing fat, having excess fat here, visceral adiposity around and in front of your stomach, right, your intestines, especially your liver, seems to be predictive of developing type 2 diabetes and cardiovascular disease. Okay. So if you have excess fat, if it is in places that is not here, theoretically that's better. But that's kind of that's why adding the waist circumference measure is helpful.
So waist size is obviously also just related to like overall body size. Is there more data that would explain the difference between like someone who's 5'5" and their natural waist size is like 30 versus like someone who is like 6'6" and has like already a 38 or something?
No, but that height will be taken into consideration when you're actually calculating their BMI.
Okay.
The height is in that equation.
Becomes slightly less predictive there.
Again, when we say predictive, like you just put everybody in and you have hundreds of thousands of people and you just dump everybody in. This is the number that matters. 40 is the number that in general seems to matter. Okay. And that's not pant size, right? That's actual measure of waist like circumference. Okay. Good questions. All right. Well, then let's talk about composition. Okay. When we try to quantify what you're made up of, what we are doing is dividing you into the individual sort of chemical or anatomical components, the tissue that you're made up of. All right. And there are several ways that this works. There are several ways that we do this, but it all begins to derive from one very clear kind of initial thing. Okay. And that is separating you into adipose tissue or fat, and then everything else. Fat mass, everything else. All the other stuff that we do about different ways we quantify things, which ones are more or less accurate, all has to do with what happens in that fat-free mass component. Okay? Fat-free mass means bone, water, minerals, right? Muscle, protein, that kind of stuff. Okay? There's lots of different models. We'll go through a few of them, but almost all of them, when they differ, it's all about how we handle the fat-free mass portion of things. So things to understand here, okay? When I say fat mass, I mean all lipid material in your body, all of it, okay? All of it. There is this concept of something called essential fat. We have no idea what the number is, but we know that everyone has some baseline level of lipid tissue in your body that is absolutely necessary for you to be alive. Okay? We can't really figure out what that bottom end number is because it's not ethical, right? Just like lock you in a room and basically starve you to the point and like DEXA you every day until we figure out where that point is at the end of things, right? It's like the terrible plot of a Saw movie or something, okay? We estimate that essential fat is somewhere in the 4 to 5% range for men, okay? And about 8 to maybe 10% in women. It's higher in women because of childbirth, okay? If you are a man and you have 4% body fat, you have no fat. None. A woman who's at 10%, you have none, okay? None. So we have to recalibrate how we think about these things. You'll hear people say like, oh, he's like 2% body fat. Dude, no, he's not. He's not 2% body fat. Okay, he's not. Put him in a DEXA scanner, he's probably like 10 or 11 or something like that. So we just have to recalibrate what these numbers are going to mean. Fat-free mass is all non-lipid tissue. So it's body mass minus fat mass. So all lipid tissue subtracted out of body mass. Lean body mass is theoretically, although it's not always used this way, but lean body mass is supposed to be fat-free mass plus essential fat. Sometimes you'll hear lean body mass referred to as water and muscle. It's just going to vary. The DEXA gives us some weird numbers, but that's generally where we are. Lean body mass and essential fat cannot actually be quantified because we can't quantify essential fat. Okay? We throw these terms around and they have a theoretical meaning for us, but we can't put a hard and fast number on them. Okay? Okay. So we're going to start, and this, I wish this graph went the other direction, but we're going to start over here on the right. Okay. When we are measuring body composition, we've got fat mass and fat-free mass. That is this idea over here on the right. It's what we call a two-component model of body composition. Fat mass, everything else. Okay. Here, two-component model. Many of our ways of measuring body composition, things like skin folds, something like bioelectrical impedance, is a two-component model. You get fat mass, you get everything else. Okay? So that's what this looks like. Now, as we work our way to the left, which I know it's going backwards in some ways, there's this binky two-component model, which is fat mass or fat, essential fat, and then lean body mass, which again, right, we're not using this term correctly. Lean body mass is supposed to be fat-free mass plus essential fats. I told you guys we use lean body mass in a real weird fucking way. Okay. But it's basically there's essential, and then there's everything else. Okay. Then in our more complicated and sophisticated models, we could try to do an anatomical model. This is what we have used to essentially validate all of our measures. Okay. You guys did this in anatomy class. You do an anatomical dissection and we say there's adipose tissue, there's muscle, there's organs, there's bone, there's everything else that's left. Like we legitimately dissect a cadaver, tease out every individual tissue, classify it as something, weigh it out, right? And then we can figure out what percentage of your total body mass is made up of those individual things. That has been done. Okay, that has been done. Another way to do things would be to do the same thing, do the dissection, but then we split you into the chemical makeup. There's fat, there's protein, carbs, water, mineral. Okay. And so some of our more sophisticated ways of quantifying stuff are going to play around between the anatomical and the chemical models to try to let us get a little better understanding of what's going on inside of our fat-free mass. Okay. Does that part make sense? Okay. Most things are 2-component models. I'll explain to you guys, DEXA is actually a 3-component model because you get fat-free, what we call lean tissue, so basically muscle, organs, water, and then bone. And then there's one that's called a 4-component model where we get a little bit of everything. We get fat, we get fat-free, we get muscle, we get body water, and we get bone mineral. And so I'll walk you guys through how that's going to work. Okay. So when we assess things, we're going to go through a few of these. There's a direct measure of body composition. I cannot do that in any of you. I cannot directly assess your body composition because that involves an anatomical dissection. Okay. Now, if any of you want to donate a finger, it's okay. It's fine. We'll take a finger, I guess, but we can't do that. When we have done all of this, as I said, people have dissected cadavers. They will take the cadaver, they'll scan the cadaver in a DEXA, they'll scan a cadaver in an MRI or a CT machine, they'll take skin folds and they'll do things like that. Then they will do the dissection and they'll sort of figure out how we can make those things work together to help us. So a lot of our things have been validated off of anatomical dissections of a very small number of cadavers. Okay. We can try to do a chemical analysis, determine the weights of different types of molecules comprising your body mass. Again, can't really do that because you're alive. Okay. So all the things that we think of as body composition are indirect measures. The primary thing that a lot of them are based upon is something called densitometry. And I'll talk about densitometry a little bit later, that if we know the mass and we know the volume of a tissue, we can calculate its density. And if we know its density, we can figure out what you're made up of. There's high resolution imaging like MRI and DEXA, okay, that are very accurate but very expensive. We can take a skin fold, which is mostly based upon densitometry. You can take a bioelectrical impedance. Again, it's mostly based upon densitometry. And I put BMI on here. And again, I want to remind you that BMI is helpful from a health standpoint, not a measure of body composition. Okay. So we'll get into a little bit of what densitometry is, and then we'll dig into a little bit of what we know about each of these kinds of things. Okay. Okay. For many, many years, densitometry was the gold standard. This was the best way for us to quantify your body composition. The idea behind densitometry at its most basic is you are made up of fat and non-fat tissues. Okay? Fat has a known density. All of your non-fat tissues have a known density. Okay? If we know those densities, I can basically figure out your mass and your volume, I can determine based upon your overall density what your body composition is, because we got to slide those things up and down to get to that number. Okay. Originally we get our body volume. Okay. And our idea of densitometry through something called underwater weight. Okay. When you have a small child, this becomes very obvious. Small child fills the bathtub up every time she takes a bath, right to the very, very top of things, and then she wants to jump in and splash around. Guess what happens to the water level when it goes from being empty to putting a rather large 6-year-old in it? It rises, right? That's the idea of densitometry. The water, you have a known volume of water. You put something in that water. If it's dense enough that it sinks, it displaces a certain amount of water. And so you can measure by how much the water rises, you can get an estimate of the volume of the object that went in. So Ellis jumps in the bathtub, The water rises, we make some marks, we measure all of that, we know then how much it went up, how much did the volume rise. We can say Ellis occupies X amount of volume. We also know what her body mass is. We can use those two things and calculate a body density, and we can estimate then sort of what she's made up of based upon all that. That's the general idea. Okay. The idea of all of that is something called Archimedes' principle, right? Archimedes' principle. I don't know if it's a real true story, it's a fable, but here's the crown, right? Is the crown made of gold or something that was less valuable? Each individual metal has a certain density, and so you can put it in the water, see how much water it displaces, and figure out from there kind of what else is going to happen. Okay? So, the density of fat is 0.9 grams per cubic centimeter. That's its density. Muscle has a density of 1.1 grams per cubic centimeter. You put fat in water, it floats. The density of water is 1 gram per cubic centimeter. You put fat in water, it floats. You put muscle in water, it sinks. You put bone in water, it sinks. You put water in water, what happens? It's just, the water level goes up. Okay? So you have a certain amount of fat in your body. You have a certain amount of protein or muscle in your body. You have a certain amount of bone in your body, a certain amount of water in your body. All of those things get added together. Okay, they get added together and they determine your overall body density. And so most of you have a body density over 1, right? But the extent to which it gets over 1 is based upon more fat, it pulls it more towards 1, more muscle, it pushes it more towards 1.1, more bone or bone mineral density, it pushes it way over on the other side of that. Okay? That's the general idea. You all have seen and used an equation called the Seary equation. Okay? The Seary equation is that percent body fat is equal to 495 divided by your determined body density minus 450. Okay? That's the Seary equation. We use the Seary equation if we do underwater weight. We use the Seary equation if we do skin folds. I think in some levels we use the Seary equation in the background when you do bioelectrical impedance as well. Pretty much anything that is based upon densitometry, you're going to come out of way, calculate a body density, right? And then plug it into the Seary equation. And the equation works fine if you're in the middle. It's not great if you're way off on sort of either. Okay.
Do we calculate anything on the exam?
As of today, I don't know. I do not know off the top of my head. I'd be like, hey, Ty, will you look at the test and tell us? But Ty's not here. So if you need to calculate something, we'll give you an equation to do so. Okay.
We don't need to memorize the equations itself.
It would behoove you to know that the fat is less than water, right? And that muscle and bone are more than 1. So fat floats and these other ones sink. Okay. There.
Sorry, but I forgot. Is the final exam or like the last one that we have cumulative?
Yeah.
Or just
Just new stuff. Just new stuff.
Going there on like the final week?
Yeah, it's during finals week. We will take it. I don't know. It's like Tuesday morning at 8 or something crazy. But it will just be a regular test on the new stuff. Okay, here's a fun one. Here's Jack and Dave, or what I call Dr. Black in college here. Dr. Black now, here, in the midst of all of this. Jack and Dave are identical. They're the same height. They weigh the same. They do not weigh the same underwater. Okay? Jack, unsurprisingly, weighs more underwater than Dave does. Anybody want to guess why? Muscle, right? Jack has more muscle as total weight than Dave does. So, more muscle, muscle's more dense than water. He sinks, therefore he weighs more underwater. Dave over here, right? Dave over here, a little more daddish in some ways, has more fat. Fat wants to be more buoyant, so therefore he weighs less underwater. And this is the idea behind densitometry. Okay, when we do this truly, what we do, we're not measuring the volume of water you displace. By measuring how much you weigh, we can get a much more accurate sort of estimate of body density by doing all of this. Okay. We're trying to decide, anybody, I don't know if it's in testing and prescription or if it's in exercise physiology lab. Anybody, do y'all do this still? Anybody had a chance to do this? In Dr. Larson's lab, we have, I call it the Silence of the Lambs tank, but we have an underwater weighing tank. It's like just a giant hole in the ground that goes down like 15 feet. We fill it up with water and then you hop in. When I was a student at Georgia, we had it was an above ground tank made out of plexiglass. So you had to get in and everybody could see you. And so we can still do all of this. For the longest time, this was the most accurate way for us to try to quantify body composition. Okay. Okay. So while it's accurate, there are some limitations. One, it's a difficult and time-consuming procedure. You have to blow all the air out of your lungs that you can, hold your breath, and get dunked underwater for about 30 seconds. Which I'm not going to lie, freaks some people out, right? If I'm going to tell you, hey, Veer, go, now hold your breath, right? Mentally, it's kind of a difficult thing. There's variation between people in their makeup of their fat-free mass, in protein and mineral and water. It's a two-component model. And we're going to treat everything the same. So that's going to be one of the limitations. Bone density varies and total body water varies. And so it's not as valid a measure in kids, in women, the aged. I'm not quite aged, but I'm rapidly approaching that, and some athletes. It works great in normal average people. Okay? In normal average people. So how can we make these estimates more accurate? So we can take this idea of densitometry. If we know that we're composed of fat and water, mineral and protein, we could try to quantify each of those rather than just fat and fat-free. And that eliminates some of the error. That's where if the error is in the water and the mineral and the protein, then let's try to do a better job of quantifying those. And that will give us a more accurate estimate. The percent fat estimate error in densitometry, depending upon how well it was done, is between 2 and 4%. So you do densitometry and it says you have 20% body fat. You might have 16, you might have 24, or somewhere kind of in that range in the midst of all of those. Okay. So it's good, but it's not our absolutely most accurate one. Okay. So as we try to make these estimates better, here's our densitometry, fat mass, fat-free mass. I'm going to show you guys this molecular model, which is a way that people develop to try to do things. We call this a 4-component model. We're going to get bone mineral, we're going to get protein, we're going to get fat, we're going to measure body water. By measuring each of these things, we can make a much better assessment and wash out some of the error in estimating fat-free mass. Okay? When we do a 4-component model, you do UWW, since we do underwater weighing. We get a body density from underwater weighing. We do a DEXA scan, which I'll talk about in a minute, to get bone mineral density. Okay? And we use bioelectrical impedance to try to measure total body water. Other ways to measure total body water is we can do something called deuterium dilution. We give you radioactive water to drink. It's not that radioactive. It's not really radioactive. It's just radio-labeled water. And we can do deuterium dilution and get a very accurate measure of body water. So we can quantify body water, we can quantify mineral, and we know from densitometry then what our fat-free mass is. We can then use that to estimate what's left is going to be protein, and we already know what the fat portion is. So it gets us a much better estimate. The problem with a 4-component model is it's time-consuming and it's expensive, all for an extra like 1 to maybe 2% increase in accuracy. Okay, so from a research perspective, this was something that people did. It's better, but in a very practical sense, in the real world, the kind of reward from doing all of that extra stuff may not be that great. Okay. And so you get sort of this equation, the Siri equation for the 4-component, which you don't have to know, right? But you can just see that there's a density measure from underwater weighing, there's body water from bioelectrical impedance, and right, there's muscle here, or mineral, sorry, not the M is for mineral, from DEXA. You put all of those in and you can get a number. Okay. So you can do it better because you're getting a better estimate of the things in fat-free mass where the error exists or where there's differences between people. But we don't really do this anymore. You can't go to the hospital and say, "Hey, can I get a 4-component model of all of this?" Athletes aren't getting this done, right? To see is training changing this or that or something else. We're not doing that. Okay. But it is theoretically better. And I think it shows where the error in the 2-component model exists. Okay. Okay. Let's talk about what we typically do now. Okay. Probably the most accurate and most commonly used way to get body composition now is DEXA. It's just a fancy X-ray. It's just a whole body X-ray. DEXA stands for dual energy X-ray absorptiometry. Okay. DEXA is a 3-component model. 3 components. We get fat mass, we get bone mineral or bone mineral density, and then we get everything else, which DEXA calls lean soft tissue, which is water and muscle and organs and things. Okay. There's very good agreement between percent fat from DEXA and percent fat from the 4-component model, as well as from anatomical dissection. The cool thing about DEXA is it allows for estimation of muscle in individual arms and legs. Okay. As part of Ty's thesis, we're doing DEXA scans on people, and then you take the DEXA and you pull up the person's DEXA. We draw a box around your quad, and it tells us how much muscle's in your quad. Technically, it tells us quad and hamstring, but sort of the upper sort of thigh area. So you can get individual limbs if you want to on all of that. This lets us have a much better estimate of regional fat and muscle or lean tissue distribution than underwater weight. And it can tell us where in your body is the muscle, where in your body is the adipose tissue. Is it in a good place? Is it in a not so good place? If you change body composition with diet or exercise or something else, right? Is it changing in the places that we were wanting for us to be able to do? The other really important thing is this is how we know, ladies, what your bone mineral density is. Every one of you in here should go get a DEXA scan now, today, right? So you know your bone mineral density is probably very close to as high as it's ever been or it's ever going to be. It's useful to know what it is now because it's individualized to you so that as you age, you can get additional scans and have some better sense and handle on to what extent is it changing or not changing. Okay? So this is the big issue. This is how we quantify if you have osteoporosis. You go, you get a DEXA scan. We have normative values for sort of a large group of women. And if your value falls a couple standard deviations below the normative values, then we say, okay, here it is. The DEXA we can also look at, and you can see, let me see if it shows it in our pictures. You get a DEXA, we get this kind of ghosted looking picture where we see your bones. And you guys know it's kind of hard to see. You can see the lean tissue of the thigh, of the calf, and things around them. Where the bones look brightest, greater bone mineral density. Okay? How many of you have broken a bone? Okay? Look at this and tell me if the bone you broke is really bright or one of the more dim ones. How many of you broke your arm or a finger or something? Yeah, okay. How many of you broke your fibula? It doesn't even really count. You could just kick your neighbor and break their fibula. It's so small, right? Anybody break a femur? No? What about a tibia? Anybody break a tibia? Like one? Okay. Why? Well, one, they're big. They got a lot of bone mineral density because you load them a whole bunch. Look at the hands. Why do people break their hands and their wrists and their lower arms? Because they have the lowest bone mineral density. We have all kinds of wild data on this. One of our former faculty members, she was very interested in bone health. And they did all of this in soccer players. You know, in soccer players, which leg and which hip has the highest bone mineral density? You're non-dominant. Because you load and you stand and then you kick with the other leg. They do this in cyclists and in rowers. And cyclists have reduced bone mineral density compared to runners, especially in their legs, because it's non-weight bearing. They don't ever bear any weight on their legs. Big, strong, active people, and they have low bone mineral density because of all of that. Right? Same rowers, it's not so bad because they push with their legs, but you get like one side to the other where the forces are applied. It's kind of some crazy stuff. Okay. So that's what a DEXA scan is going to look like. Here we can zoom in at the hip. You can zoom in the spine. And when you look at osteoporosis, hip bone mineral density is really important because you're going to fall, you're going to break your hip or not. And then stuff in the lower spine are areas that are very, very highly affected by kind of whatever's going on there. Okay. Okay. We'll finish off by doing a quick thing about an MRI. And then we'll finish the rest of this on Wednesday. An MRI, I'm going to say this, and I want you all to be very careful about what you write down. Of the things that are available to us that are not anatomical dissection, MRI is the most accurate estimate of body composition. Okay. It's also wildly infeasible. Okay. If we had several hours to do a whole body scan on you, and then we had months to let a poor grad student quantify and circle out everything in the images, we could get a hyper accurate estimate of things. Okay. But MRI stands for magnetic resonance imaging. And what you do is they put you in the scanner, they turn the magnet on, and all of the electrons in your body line up facing one direction. Then they turn the magnet off, and the electrons go back to their sort of original kind of baseline configuration. And electrons in different atoms process back or recess back in different time frames. And so based upon those differences, we can create these images of different tissues being made up of different things. It's very, very accurate. Very accurate. Outrageously expensive, right? You go get imaging done today, your insurance company will pay about $2,000 an hour to be in the scan. If we did a total body scan on me from my toes all the way to the top of my head, I'd probably be in the scanner 6 or 7 hours straight. Don't move, sit there, right? It's awful. But very expensive, but very, very accurate. Then it would take us 6 months to analyze all the images because there would be so many. It's crazy. But what you can do is you get these cross-sectional slices like x-rays at various points. And if we get one like in the stomach, one like in the chest, one in your thigh, like we can get 2 or 3, much more easy for us to quantify. We can get some pretty good ideas of kind of what all's going on. So MRI is much more helpful for smaller localized things than for total body stuff. Okay. All right. We'll stop here. We'll pick up on Wednesday with everything else.